So this comes from the review questions that were linked up in the announcement. I'm not going to do every single one, but I'll do just a couple samples. So the first one I'm going to do is number 51. This is actually the one from chapter 16.51. Okay, so this says we got lactic acid, and it's got a really long formula. However, I'm going to be lazy and just write HA to represent that weak acid. And I know that if this is weak, that it dissociates to H plus and A minus. They tell me that the initial concentration is 0.1 molar of that lactic acid. Anytime you have a weak acid, almost guarantee you're going to have to do a Rice chart, or at least understand how to apply a Rice chart. And so most cases, our Rice chart is going to look exactly the same. Something like that. We can also write our Ka expression, where we do products over reactants, like so. And ultimately, what this question's asking us to solve for is the Ka, which means I need to know, I need to have values to plug in for these three variables. And right now, I kind of do have things I could plug in, like normally we would plug those things in for those three variables. However, I can't have Ka as an unknown and X as an unknown. So I need another piece of information to be able to determine what X is, so that I have numbers that I can actually plug in for those concentrations in the K expression, so I can then algebraically just solve for Ka. And we are told what the pH of this solution is. So that is given to us in the stem of the question. Well, if we know the pH, that allows us to determine the concentration of H plus, which we're using an X to represent that. So that's easy enough. We just do 10 raised to the negative pH, which gives us 3.6 times 10 to the negative third molar. That's the hydrogen ion concentration. And so now that I know hydrogen ion concentration, which is equivalent to X in my Rice chart, my ICE chart, then I can plug in here. And we've spent some time talking about this particular X and how we call it negligible. The reason we would call it negligible would be to eliminate the need for using the quadratic equation. And the reason that's okay is because X is usually a really small number compared to 0.1. And I mean, that's the case here. 3.6 times 10 to the negative 3 is really tiny with respect to 0.1. However, if you know what X is, there's no need to call it negligible. You can just go ahead and plug it in. So I'll make those substitutions. 3.6 times 10 to the negative 3 for H plus. Same thing for A minus, because those are in a 1-to-1 ratio. So we'll square this on top. And then on bottom, just substitute that in and solve. So whatever that is. Divided by 0.1 minus 3 minus 6. I get like 1.4 times 10 to the negative 4. So that is how you could solve for Ka of a weak acid given pH. The next question I want to look at is 59. It says calculate the pH of the following solutions, and then the Ka and Kb values are given in Appendix D, which I linked, or I copied that page in the handout. If this was a test question, whether it's a test in my class or in on the AP exam, the Ka or the Kb would be provided to you. They would not expect you to look that up in an appendix. So I'm just going to do two of these. We'll do 0.095 molar propionic acid, and they give us the equation for that, C2H5COOH. Again, I'm going to be lazy, and I'm just going to call this HA, weak acid HA. And when a weak acid dissociates, it pulls apart like that. They told us that the initial concentration is 0.095. We'll set up our rice table. Go ahead and write your K expression. And it is perfectly acceptable to be lazy and use HA instead of writing out the full equation. College Board would accept that. The readers would understand what you mean by that. All right, so keep in mind that we're solving for pH this time, which means we need to know what X is. And so X is going to be our unknown instead of Ka. That's why they tell us to look up the Ka in the appendix. Ka for propionic acid is 1.3 times 10 to the negative 5. So I'm just going to make those substitutions. That's my Ka. I do not know what X is, so I'll do X squared on top and then the original concentration on the bottom. I'm going to call this X negligible, and I'm going to tell the reader that I did that. So I'm calling that one negligible. I'm going to algebraically solve for X. 5 times 0.095, and then the square root of that. And I get 1.1 times 10 to the negative third. So that is not the pH, but that is the concentration of hydrogen, which from there I can figure out the pH to be some number between 2 and 3 if I'm making a prediction. And so negative log of 1.1 times 10 to the negative 3 is 2.96. That is our pH of that solution. All right, I'm also going to do C because B is almost identical, just with different numbers and a different Ka. But C is not an acid. It says we're going to find the pH of 0.120 molar pyridine. They don't tell us that this is a base, but they do give us the equation for that. And remember, I've mentioned that if you see a nitrogen, it's a pretty good indication that you're working with a base, because if we were to draw the Lewis structure of this nitrogen is going to have a lone pair on it, which is a great location for the acceptance of a hydrogen. So if this can accept a hydrogen, that hydrogen will park on that lone pair of that nitrogen, making this a base, which means I'm going to be doing Kb. And I'll have to look up the Kb for pyridine. Obviously, if this was a question on an exam, that would be provided to you. The Kb is 1.7 times 10 to the negative 9. Now, here's the thing with bases. We practice a lot with acids because it's just that's most common what they give you. And then I do just a couple bases with you guys. But remember up here I said it's perfectly okay to be lazy and call this HA. Well, we're also being lazy because we're not showing that this is taking place in water. And that's fine when it's an acid. But when you have a base, it's kind of important to include the water in that dissociation equation, because bases accept a hydrogen. But if you don't put the water in there, then it's difficult to see where the hydrogen is coming from. And so instead of just writing this thing dissociates to something, I'm going to say it dissociates in the presence of water, and I would include the water in the equation. And then what happens is this base picks up a hydrogen from that water, making C5H5NH+, and then hydroxide. So not only is it important to include the water because you need to see where the hydrogen's coming from, but we also need to see the appearance of this hydroxide. And if you don't have that hydroxide there, then it's going to be hard for you to calculate the pH, because ultimately this is what we're going to solve for in our rice chart, and then we're going to use that back in the diamond to determine what the pH is. So for this guy, since I'm producing hydroxide, I'm going to write a Kb expression. It doesn't really change anything. It's still products over reactants. Oopsie doop. And of course, water is liquid, so we don't have to include it. And we're not going to do anything with water in our rice chart because, again, it's liquid. We only use gases, an aqueous substance. So they tell us that this is 0.120. From here, the rice chart looks the same. So now I can make some substitutions. KB is 1.7 times 10 to the negative 9 equals x squared over 0.120. I'm going to call that x negligible and tell the reader that I did that. So I'm letting them know, like, I didn't forget to include it. I know that it's negligible because it's so small. Algebraically solve. Negative 9 times 2 square root. And so I get that x is equal to 1.4 times 10 to the negative 5. Now keep in mind that x in this case, because this was a base, is the concentration of hydroxide. So when I want to go back to the diamond to figure out what the pH of this is, it's not just simply the log, the negative log of this number. pH is 14 plus the log of hydroxide concentration, which is what I know. So when I plug that in, log of 1.4 E negative 5, I get that the pH is 9.15. So there we go. And I guess this should really be 9.146 because we had 3 sig figs at the beginning. All right. Next, I want to look at a buffer question, which was in chapter 17. And so if you look down, there's number 22. It says calculate the pH of a buffer that is 0.15 molar in NaHCO3 and 0.125 molar in Na2CO3. And anytime, specifically in acid-base type problems, anytime you see sodium or anything from group 1, guys, those are fully soluble, which means this thing is going to dissociate and sodium is going to be a spectator ion. And so it's not the sodium that I care about, it's the other ion. So in this case, it's the HCO3 minus and the CO3 2 minus that are going to be producing the buffer. Those are the two ions that are making the buffer or doing the buffering action. Sodium's there, it's just not really participating. It's not doing any of the neutralizing. And so there's different ways you can solve buffer problems, but I really like Henderson-Hasselbalch. And this equation is on your formula chart. And so remember, in order to make a buffer needs something weak, whether it's an acid or a whether it's an acid or a base, and it needs its conjugate pair. So whatever the weak thing is, it also needs the conjugate to that weak thing, and that's what produces a buffer. And so A minus represents the conjugate base to the weak acid, HA. And so that's why this formula works. So up here, HCO3 minus is acting as the acid because it has the hydrogen to donate, and CO3 2 minus is acting as that conjugate base to that acid. So I already know what concentrations I need to plug in. I'm simply making a substitution into this equation. The last thing I need to know is the pKa. Again, if this was a test question, whether for me or for AP, they would either provide you the pKa or they're going to give you the Ka. And then you just have to know how to treat that Ka. So the Ka for this acid, this HCO3 minus acid, is 5.6. 5.6 times 10 to the negative 11. So you would not have to be able to look that up in an appendix. That would be provided. But I need to turn that to pKa. Well, anytime I put p in front of something, that just means take the negative log of that number. And I believe when I do that, I get 10.25. So 10.25 is my pKa. I have my concentrations for both my A minus and my HA. And so I'm just going to plug all those numbers in. Plus the log. A minus, remember, is the conjugate base, which is the CO3 2 minus. So that's 0.125 on the top. And then HA is the acid, so that's 0.105 on the bottom. And before we even calculate this, I want you to understand conceptually, this term right here is bigger than 1. Like this fraction is a number larger than 1. When I take the log of a number larger than 1, this whole thing is going to be some positive value, which means I'm going to add something to 10.25. So I would expect my pH to be bigger than my pKa. If this term was less than 1, then this whole log term would be a negative number, meaning I would be subtracting something from 10.25 and my pH would be less than 10.25. So when I just type that in the calculator, I get 10.33, which is exactly what I expected. I expected my pH to be greater than my pKa because this ratio is a ratio greater than 1. Okay, the second part of that question says calculate the pH of a solution formed by mixing 65 milliliters of 0.2 molar NaHCO3 with 75 milliliters of 0.15 molar Na2CO3. Okay, so we already know we have a buffer when we mix these two things together because we just kind of worked out the initial concept of we can produce a buffer that has a pH of 10.33 if we mix these molarities together. Now they're specifically telling me a particular volume of a concentration. And so what I have to do in this situation is instead of just plugging these concentrations in to this ratio, I need to know how many moles of each of those things I have. Like this is a mole ratio. And if these molarities, like if I'm given this but no volume, then I'm assuming this is like in the same volume. So these volumes are the same, which means it's okay to plug in those numbers here. But now the volumes are not the same. This is not the same volume. So I need to figure out how many moles. So that's easy enough. Take the molarity multiplied by the volume. That's going to tell us how many moles we got. So 0.2 times 0.065 tells me that I got 0.013 moles of this HCO3 minus, my weak acid. Remember, sodium's a spectator. I'm going to do the same thing with my conjugate base. So it's 0.15 molar times 0.075 liters. So I got 0.01125 moles of the CO3 2 minus. And so now that I have the moles, I can set up the mole ratio here. Now I can convert this back to volume. If you convert this back to volume, that's fine. Just remember that it's the total volume of that mixture now, so you'd have to add those together. But since I'm setting this up as a fraction and the volumes are the same for both the acid and the conjugate base, that volume calculation is going to cancel itself out mathematically. And so you can just plug moles in and save yourself the step. So we're trying to find pH. We already calculated pKa for this acid. Then we're going to go log of the conjugate base, A minus, which is this guy, 0.01125, over the weak acid, which is 0.013. And this ratio is less than 1, which means this term is going to be negative, and so I would expect my pH to go lower than my pKa. And when I calculate that out, I think I get 10.19. So that is a buffer. All right, the last one I want to look at is 1741. I'm not going to do all of these, but it says how many milliliters of 0.0850 molar NaOH is required to get to the equivalence point for the following mixtures. And so it says, what if we got 40 milliliters of 0.0900 molar HNO3? How many milliliters of base do I need to add to get to the equivalence point? Now remember, equivalence point is where moles of acid equal moles of base. It does not matter if it is a strong acid or a strong base. The equivalence point happens when moles of acid equal moles of base. And we know that if we take molarity and multiply it by volume, that is the same as determining moles. That's algebraically like canceling out so that we can solve for moles. So moles of acid times volume of acid, molarity of acid times the volume of acid should equal the molarity of the base times the volume of the base. Well, I know 3 of those variables. So HNO3 is my acid. Tells me that my molarity is 0.09. My volume is 40. You can convert that to liters and then go back to milliliters, or since we're looking to solve in milliliters, you can leave it in milliliters. Just be consistent with your unit. And then we know the concentration of our base to be 0.0850. And we're trying to figure out what the volume of the base is, how many milliliters. So you just, easy enough, solve, divided by 0.0850. And this looks like it would be 42 let's see how many sigmas. We got 3, so 42.4 milliliters of base needed to get to that equivalence point to cause that color change with our indicator. And so there's a B and a C to that, same kind of relationship. As long as you know that molarity of acid times volume of acid equals molarity of base times volume of base, that's the same thing as saying moles of acid equals moles of base. That's by definition the equivalence point. Again, it doesn't matter if it's strong or weak. So there you go.